Hello, this is Mr. Simmons with 16.1 Kinetic Theory for ICP. All right, we're going to talk about solids, liquids, and gases, heating curves, particle motion. So, kinetic theory. Our goal is to compare and contrast the kinetic theory of matter in solids, liquids, and gases. We want to compare and contrast particle movement in the four states of matter and apply kinetic theory to the melting and boiling points of water. So, kinetic theory, to understand the states of matter, we must think about the particles that make up matter. These atoms and molecules, the particles that make up air, are constantly moving. The kinetic theory is an explanation of how particles and gases behave. There are four major assumptions in kinetic theory that number one, all matter is composed of tiny particles. Number two, these particles are in constant random motion. Number three, the particles collide with each other and with the walls of any container in which they are held. And number four, the amount of energy that the particles lose from these collisions is negligible or almost zero. So because their particles are in constant motion, colliding with each other and with the walls of their container, gases do not have a fixed volume or shape. They will take the shape of their container, so we can also say they're indefinite. They will expand and contract, so they take the volume of their container. So they're indefinite volume and indefinite shape, or do not have a fixed shape or volume. Liquid state. Some of the assumptions of kinetic theory apply to liquids and solids as well. The particles in a liquid are moving slower than gases, therefore have less kinetic energy. In our slide before, we saw that kinetic energy equals 1/2 the mass of the particle times the velocity squared. So if it's moving slower, V will be smaller and kinetic energy of motion will be less. So the particles in a liquid are moving slower than a gas, therefore they have less kinetic energy. The particles are less able to overcome their attractions to each other. So they stick together like this, like mini magnets. They can flow past one another, but they cannot expand and contract. They can slide past each other, allowing the liquid to flow and take the shape of its container. Because they have not completely overcome the attractive forces between them, liquids have a definite volume. They cannot expand and contract. So liquids, compared to gases, have less energy, probably medium energy. They have strong forces. Gases have no forces. Solids have a definite shape and volume. They are still in motion, but they just vibrate a little bit. They have so little kinetic energy that the particles are unable to overcome the attractive forces. So we'll draw a solid like this. We have these little wiggles right here. We'll do this in class. And they vibrate, but they cannot go past one another. So states of matter are gases. They tend to have low density. They're spread out. They're easy to expand and compress, so they have indefinite volume, and they fill their container, indefinite shape and indefinite volume. They have high energy and little to no forces. Liquids have a high density. They are harder to expand and compress, and they take the shape of their container, but they do not take the volume of the container. So they have indefinite shape, but definite volume. Solids have very high density, are really hard to expand and compress. They have a rigid shape. They vibrate. They cannot take the shape of the container or the volume, so they have indefinite volume and shape. Changes of state. When thermal energy is added to a solid, the particles move faster and transfer energy to other particles in the solid. So melting and freezing. The melting point is the temperature at which a solid becomes a liquid. Energy is required for particles to slip out of the ordered arrangement of a solid. Freezing is the reverse of melting. So as we add energy, the solids turn to liquids and liquids turn to gases. As we take away energy from the system, they tend to get colder, and so they go from gas, liquid to solid. When a liquid's temperature is lower, the average kinetic energy is decreased. The particles become fixed in position. The freezing point is the temperature at which a liquid turns into a solid. So here we have a solid. We add energy. They tend to jumble up. They have more randomness, more entropy. We add more energy, they turn to gases. If we take away energy, the gases turn to a liquid and then eventually to a solid, becoming more ordered, and they have less entropy, less randomness. When particles that make up a liquid are moving fast enough to escape the attractive forces of each of other particles, they enter the gas state. This process is called vaporization, which can occur in two ways: evaporation and boiling point, or boiling. Evaporation occurs at the surface of the liquid and can happen at any temperature. So when you're outside and it's really hot and you sweat, your sweat evaporates and takes away heat away from you, even though it's still really hot outside. Boiling occurs through a liquid depending on the pressure of the surface of the liquid. So when you boil water, you're increasing the pressure. When the pressure of the liquid equals the air above, it can pass into the gas state. The boiling point of a liquid is the temperature at which the pressure of the vapor in the liquid is equal to the pressure of the surface of the boiling. So evaporation just happens at the surface, but as you start to boil water, the pressure all through it becomes all right, so when you're boiling water, you increase the pressure. When the pressure of the water equals the pressure of the air, it can change from liquid to gas. Condensation is the reverse of vaporization. So vaporization is going from liquid to gas. Condensation is going from gas to liquid. So right here we have water condensing on a windshield or something. We have water condensing on a spider web. But sublimation is the process of a solid changing directly to gas. So during Halloween, you see people drop dry ice into water and it turns into a gas right away. That's an example of sublimation, going directly from gas or solid to gas. So here's an overview of what we just talked about. If we go from ice to steam, ice has a melting point, turns into water, it evaporates or vaporizes, turns into steam. To go reverse, so we're adding energy as we go this direction. If we go the reverse direction, we're taking away energy. So if we have hot gas, we take away energy, it condenses into water, and then once we take away energy from the water, it will freeze or solidify into ice. If we go directly from ice to steam, we have sublimation or sublimates. If we go from steam to ice, we have desublimation. So heating curves. Heating curves show how temperature changes over time as thermal energy is continuously added. And so right here is an example of a heating curve. I think we'll see in the next one. Yeah, we'll look closer at just a second. So notice that the temperature at the position B and D do not increase even though thermal energy is being added. The energy added at these sections are being used to overcome the attractive forces between the particles. So we talked about a little bit about forces earlier on, where solids have really strong forces and liquids have medium forces. So let's look a little closer. The energy added to these sections are being used to overcome the attractive force between the particles. We just said that. So if we have a solid, we're going to add energy. So as we go to the right, we're adding we're heat energy. As we go up, that's temperature. So we're going to add energy to a solid. It starts to warm, it starts to melt, and see it flatlines. Even though we're adding more energy, the temperature stays the same. That's an important property. So the temperature will not go up during when it melts or freezes, or go down when it freezes, because the energy is being used to separate these molecules, not to make them go faster. And then the liquid starts to warm again, it's heating up, and when it starts to boil, when it vaporizes into a gas, once again the temperature stays steady, even though we're adding heat energy. Heat energy is also the spacing of the particles. So here we're spacing the particles out, but they're not going faster. And so we have these flat lines right here. So we have solid, liquid, gas, and in between those phase changes, if you were to measure the temperature as it went up, you would see a flat line. A flat line here, just because the energy is used, the heat energy is not used. Temperature is how fast the particles are moving. So even though we're adding heat, the particles aren't moving faster; they're just spacing out more. So over here, there's a big heating curve. So this would be position A, B, C, D, and E. So position A, we have a solid only. At position B, we have the melting point. So you can see the temperature is not going up, or freezing if you're going from C to A. Here's C, liquid only. So once again, the particles are moving faster and faster and faster, and then all of a sudden it flatlines again when it goes into a phase change, when it's vaporizing, which could either be evaporation or boiling, and then it turns into a gas in E. The plasma state is our fourth state of matter and is actually the most abundant in the universe. Plasma is matter that has enough energy to overcome not just the attractive forces between its particles, but also attractive forces within the atom. So we'll learn here really soon that we have protons and electrons and neutrons within an atom. They have these forces. And so there has so much energy, plasma, that actually strips away the positives, negatives, and neutral particles. So the electrons are completely stripped off the atom. So here's a look at a solid. A solid is going to be regularly arranged in definite volume, definite shape, very low forces, but very strong forces, but low energy. A liquid here, it has definite volume, so it's not going to expand and contract, but it has indefinite shape. It can move past, it can flow like a fluid. Um, and it's going to have medium forces and medium energy. Gases here have very high energy, but very, very, very low forces because they're moving so fast. And they have indefinite volume, indefinite shape. And plasma is a little harder to study. You'll see it in lightning and in the sun. Um, Plasma is where the internal forces of the atom, the attractive forces of the atom, are overcame by the amount of energy it has. So plasma is the most abundant state of matter in the universe because all stars are made of plasma. Thermal expansion. The particles in matter tend to move fast and expand when heated. Thermal expansion is an increase in the size of a substance when its temperature is increased. Matter tends to contract when it's cooled. So concrete is a great example. So after every winter, we see a lot of cracks in our roads and potholes, and it's because of the concrete expanding and contracting with the change in temperature, and also water getting into the concrete. So concrete is an example of a solid that tends to crack due to thermal expansion. So as we add heat, matter tends to get increase in volume. As we take away heat, it tends to contract in volume. Thermometers are a common example of a liquid that takes advantage of thermal expansion. So as we add heat, the it used to be mercury, now it's alcohol, expands throughout the column and goes up, and we use these graduations, these lines, to figure out the temperature. Hot air balloons are an application of gases undergoing thermal expansion. We heat the gas, it becomes the volume goes up, becomes less dense than the air around it, and starts to rise. Water acts like most matter and expands and contracts as thermal energy changes, but something really weird happens at 4 degrees Celsius. Because the water's high polar end, so in biology you learn that water's sticky. We have like a negative region around the oxygen atom and positive regions around the hydrogen atoms. They like to stick together and form these little bonds. So right here, it's like mini magnets. When it's ice, they form a rigid structure, but when it gets so cold, water tends to expand under 4 degrees Celsius, becomes less dense, and floats. And that's it, guys. Have a great day.